Good evening, everybody. This is Obi-Wan Piz for n-Simplex Pachinko. We are hanging out amongst a whole bunch of stuff. My desk currently is populated with the contents of my desk because my daughter wants this desk. You're getting this thing to put in its place. And it weighs about 60 pounds. Perhaps even more. We're getting it to replace this rustic piece, which is very lovely, but my mother had it. It was given to her by my great aunt. Has this lovely, sort of cranberry color to it, which she hated. She was like, God, why haven't you painted that thing? I'm like, oh, that was nice. I like it. She's like, all right, whatever. To each their own. So I'm deciding where exactly to put all this stuff so that we can move this out tomorrow. And if we get some time then, I might decide to do a construction stream. Although I think I do believe that our daughter wanted to be a part of it, so I can't really deny her that, and I don't really want her face on the internet, so yeah, so the contents of Obi's desk can be part of the stream tonight until we get somebody to ask him math questions. So here we have a jar of snow seal, still unopened. This is at least 20 years old because I had this to seal my EMT boots, which are now, all pockmarked, and the leather cracked on one pair, and the other pair is currently, it's okay, but it's not 100%. Okay, and then got my sunglasses, I'll put those away. We have one Wi-Fi card, PCI 802.11b, wireless PCI card. Originally it was in my desktop probably 3 iterations ago, because I had that for college. I had a Ralph Lauren wallet, which somebody gave me. I don't know when that came. Very nice, but mine's been serving me for many years. Like it just fine. Let's see. Crossword puzzle from like a month ago. Oh, yes. The travel game Brain Cheeser. Recommended. Interesting. It's got magnetic puzzle pieces so that you could actually use it while you're traveling. I believe they also have a non-magnetic version. I could be wrong. The goal is that you put mice, little mouse tokens, which are themselves magnetic, into certain positions on a grid, which has numbers on it. Oop, there we go, numbers. And then you place all of the cheese pieces, which have holes in certain places, where they need to go in order to solve the puzzle. So there are 8 pieces of cheese. You need to make sure that none of the pieces of cheese have holes that are like half holes are not allowed unless they're on edges. And there was something else. There's more rules, but anyway, it was a cute little game, kind of fun. Kids got into it, and we're doing it for travel, so can't argue. Kept them from fighting, so that's really important. It doesn't matter that they're necessarily quiet. It matters that they're not fighting with each other. So that was a cute game. Tickets to the Bertram. Tickets to our Arrow of Light night at our day camp program. Yeah, all of my stuff for being a den leader. You know what? I gotta put that in the recycling bin. More den leader stuff. Yay. Ooh, wait. Oh, yeah, okay. Permission slips. Oops. That needs to go to the camp. That is a $24 check. That needs to go to the camp. Yeah, I'm cleaning up my desk because my daughter wants it. She was like, when are you getting that? When are you cleaning it up so that you can take your other desk? I was like, just relax. And of course, she's, you know, 10. Still 10. Nope. Wait. Nope. 11. Oh, man. I'm horrible. Okay. Wait, no. No, she's turning 11 this year. That's right. God damn it. No, the problem was that she was in a triathlon this weekend, and it's how old you will be in December. How old will you be at the end of December? So she's in the 11-year-old category. I'm like, oh, she's 11. Yeah, no, she's not 11. Good news, this was not on my desk. One of the old compasses that I bought. Might have been given this, I suppose. You know, kind of standard fare. Look through the eyepiece at what you're trying to sight, and then you can tip your magnifying glass down so you can make sure you're pointing at the right thing. 210. Uh-oh. Oh, that's why. That part wasn't... that part wasn't secure. Let's see. Bills all paid online. Sure hope so. Found my marbles. Yep. Still labeled by me, circa 1980, whatever it was. Maybe 1990. Yeah. Always some interesting ones. we never played for keeps, really. I think too many of us were just like, that's really sketchy. So we might have traded around some of the other ones, but shooters. These are. Ooh, that almost went in my food. I really like these two here. So this one's got a shiny kind of metallic look to it, and then this one's like opalescent. It's got cool stripes going through it. Looks almost like marble. I said 1980s. Anyway, yeah, nice blue shooter. So this was the super shooter because it's actually like 10% maybe bigger than the other one. So I was always able to go out there and just wreck the field. And then of course my 1,000 other tiny ones, which almost all are cat's eye. I just really like the cat's eye marbles for some reason. It was probably just weird that it existed. And I can't remember if it was me or my brother had a shooter that was sort of dark reddish, and then when you like threw it, you know, popped it out onto the field, it would get in the sun and it would have this like deep red. Oh look, an empty. Shh. I'm sure the kids are still asleep, it's fine. Yeah, no, it must have been my brother. So I've got the two like metallic opalescent, or not opalescent, these are metallic ones, are all different colors on the different sides. And the speckled one here. Oh, that one's interesting. I hadn't noticed that. So this one's a cat's eye, but it's actually like faded, or like it never was very strong to begin with. Whereas this one is like, you know, very defined and bold in the center. So this is really kind of cool. You can sort of see it. And blue. Yeah, this is kind of your... this one's a little half and half. It's kind of interesting. So you got this like, you know, opaque side here, but then if you turn it, it's got a like transparent side. Focus. It's got like a transparent side. So you can actually turn it a little bit and shine some light through it. The marble one. Yeah, actually this one does a little bit. There. This one's brown, but still. Yeah, I also donated a whole bunch of these sets to my kids because they're making marble runs downstairs. So, like, this is my marbles set for playing marbles. Not that we actually do it. And then downstairs is the set that I had that was just in a box somewhere. It had my name on it, and they were like, "What's this?" So they opened it up, and I'm like, "Wow, it's marbles. Let's play with them." All right. They're almost all like, you know, one color, slightly boring. But I am most definitely a collector, and that might be a problem. Well, it's not becoming a problem yet. Just wait until you all see my stash of slide rules. So I only got 5. It's fine. Undo that, put it around the side. What in the hell am I doing? Alright, there we go. Just trying to tie a square knot around this thing, and it just like, because I'm upside down, it's kind of hard to compared to how I normally tie it, right? I'm like tying the square knot on the thing rather than so the way I usually tie a square knot is I am like essentially tying the thing around me. So 1, karate, and 2, that's just how I normally tie it when I tie rope. So like I was trying to tie something on something else, and so it's backwards from how I'm usually doing it. It's just bad news. Got a PSA from our county system. Drivers traveling in both directions must stop for school buses except when across a divided highway. Here's an example of a divided highway and not a divided highway. Yes, there was a picture on the next page of an example, just in case. Ugh. Imagine having to deal with, like, people. So how are we all doing tonight? I think... say I've got 2 little tiny pieces of paper here. Imagine driving. Oh, city life. We're gonna be, oh my god, we're gonna be living in England. And so public transportation is gonna be 1,000% better, at least. And then, and by 1,000%, I mean instead of waiting an hour for the bus, we'll have to wait like 6 minutes. I imagine I will be driving practically nowhere except to drop off and pick up the kids. Oh yeah, by the way. Just casually drop that. It's fine. It's fine. So my spouse got a position for a PCS tour, which is a 3-year tour with the government, to sunny England. It's not sunny there. Yep, so she got a position for 3 years. PCS, I'm not sure exactly what it stands for, but it just means, like, you know, you're going to work in a different location, usually with one of either a US facility or an allied facility. So in this case, England has several facilities that are in their country which do the same work that she does, so we're going to be moving off there for 3 years. Kids are going to be going to their elementary and middle school years, actually the exact same amount of money, but one, she is going to have to work for 40 hours a week instead of she has been doing 30 just to, like, you know, take care of stuff, and things were kind of piling up, and she was just like, this is, and I wasn't able to really pick up a lot of the slack, so she was just like, all right, I'm taking a day off. And, you know, a 4-day work week is just better, so. Oh, no. Don't I wish. No, it's the same US money, but they do pay for all of our living expenses. They do pay for, like, the kids' schooling. So normally they try to get you into public schools, but public schooling works differently in England than it does here. So, like, they don't have a whole lot of space, and everybody is trying to get into the public schools. But when you can't get into the public schools, as is often the case, you can go to a private school, which is, like, as good, if not better quality, and most people end up going to a private school at some point. Unless they need government assistance. And then, even then, they can apply for scholarships at the appropriate school if they want to do it. It's a pretty interesting system. Unlike here, where, like, you know, when the government says, hey, we need a new school, there's some land, we're going to take it. They don't really have land. Like, it's all owned. And they can't just take it. So we're going to live in probably a townhome. We're going to have the, like, temporary housing that's owned by the government for a little bit until we get our bearing, get our feet under us. We've had some friends who have been there a year already, and we're going to, like, they're not our mentor group because the friend is also my spouse's boss. So they can't be our mentors because they're also involved in, you know, the hierarchy. So. Yeah, I'll just nonchalantly draw. I keep forgetting, like, who I've told and who I haven't, so occasionally I'll throw it out there and somebody's be like, Well, that is in fact a very good question. I have practically no idea what I'm going to be doing over there. I have some ideas for a project. One of which will be to stream during more wonderful times for you European people. A second idea is to restart my channel on YouTube and start doing a project that I've been looking at to try to improve the understanding of the point and the methods that are involved in the Common Core project for the United States, but not for students, because Khan Academy and all those other people do a great job already of explaining how to do the Common Core method of math, methods of math. Oftentimes what people will disparagingly call new math because they want to call it the same thing as it was in the 70s when they were trying to do the exact same thing, you know, make it more accessible for people and explain why things were connected the way they were and all that other cool stuff. Yeah, I don't think I'm going to be streaming at 2 a.m. or whatever. No, my guess is that it would be 9 p.m. GMT. Whichever one that is. I don't remember exactly. It's either British Standard or GMT. Because those are off by one, right? What? Aren't you European? I thought you were in Germany. Oh. Were you in Germany? Hmm. Yeah, so it'd be more like 5 p.m. US East, give or take, right? So it's either 4 or 5 hours. I think it's a 5-hour difference most of the time, and then it's a 4-hour difference during that little break when one of our times switch and the other one's doesn't. It's like a week off or something like that. Oh no, it's Superbrain. That's Germany. That's right. Is 4 to 5 p.m. bad time for you? Exactly which time zone it is, but I think it's... Nope. Wrong keyboard. Yes, GMT plus 1. So it is currently British summer time. It will be earlier than it is in the US, yeah. Because again, it's going to be nighttime over there, so it's going to be mid-afternoon there. Yeah. Don't worry, I'm not streaming it to whether that be this time or that time. It's just not tenable. So, going to be working on some projects to try and expand, like I said, Common Core understanding. Sheaf cohomology. Good evening. Welcome in. My favorite thing... That, yeah, no, I understand. So, that's also going to be a tricky thing because, like, you know, I've got a bunch of favorites-ish. But then at the same time, like, at the moment, my brain just went completely blank. So, yay! Yes, that is true. We will be on the NHS. Probably within 6 months of us getting there. And then we may be able to get a an appointment with an actual NHS doctor within, say, a year of us getting there, which is potentially one of the other issues, but that's a little weird. I don't like the hand. It has been 20 years, give or take, since I took complex analysis, so Gödel's incompleteness theorem, Loim's, good evening. That's always a fun one. I do like putting Gödel's incompleteness theorem on the board in my Foundations of Math class. Now these, mind you, these are students who, generally speaking, have fairly weak math skills. And so I was like, we're doing this whole, yeah. I mean, that's fair. Grad school was not quite 20 years ago, but it was more than 15. That's just because the camera smooths out all the wrinkles. Okay. Yeah, so we get through our entire unit on logic, and then I'm like, so, does everything make sense? Like, can we solve math then in order to do all this? And they're like, oh yeah, sure, yeah, absolutely. And I was like, so what would happen if you came across a statement like this statement is false? And they're like, and I gave them the whole, very brief explanation, because again, these are students who, generally speaking, don't like math. And I was like, there's this problem that's been thought about since, the guy's name was, oh my God, Gödel. Why am I blanking? Oi. Kurt Gödel, who, came up with this idea, and I kind of explained, what I could understand about it. And, is there a set that can contain itself? Or a set, is there a set that can contain all sets except itself? Nope. Also wrong. It's the Barber paradox. Is there a set that contains all sets that don't contain themselves? There we go. We talked about the Barber paradox. We went through this and talked about that. And they were just like, oh no. I was like, precisely. And that's the point. It's that, mathematics has been thought for all these years to be so clean. I'm okay. I can think my way through most probability problems. Like, the combinatoric stuff is fine. My issue is the statistics that, like, I'm not super great on. I did calculus-based stats, and that was just like big punch in the face. But the combinatorics class that I took in grad school, and the combinatorics section of statistics, I found like very intuitive. Hmm. Yeah, we can combination and permutation if you want. And I may cut out occasionally because if I lean forward about 6 inches, it's not going to do it now. There's a dead spot somewhere in here. The receiver is literally right over here. I don't know what the problem is. But there must be some local interference that's just bothering it. So yeah, I'm decent at combination because, and Sheaf, you may recognize it from my name. So I was working at, yeah, I was working on a piece of mathematics where our students were working on your standard, right, Leroy triangle, not Pascal, yet. And their goal was to say, okay, what happens if we were to take each of these things right, and now make it a three-dimensional triangle. So, tetrahedron. And 6. Right. So their intuition was to start taking this and their intuition was to start taking this and break it into not this way actually, but to shave off the faces of each of these. This will not be face off. Shave off the front face of this particular triangle, which is just, again, your standard Leroy triangle. And then look at the thing that's behind it. So what will now show? Well, if we removed all the black numbers that are here, what's going to be left is the numbers that were behind them, starting with this 1, and then the 2 and the 2 here, 3, 6, 3 there, and so on and so forth. And this is going to be the just the second numbers. So whatever the second numbers are behind 1, 4, 6, 4, 1. So 4, 12, 4, 12, 12, 4. Yeah. I mean, like, I did put this as part of the research. I should know what it is, just kind of offhand, but it's been a while. So as it turns out, this is now a constant multiple of the original Leroy triangle. So this row here is going to be the original multiplied by 1. This is going to be the original multiplied by 2. This is going to be the original multiplied by 3. This is going to be the original multiplied by 4, and so on and so forth. So whatever you have now, you're back one row, and you've just multiplied by the number that is in this position, your n choose 1. So whatever your n choose 1 is, you multiply that by the previous row on the n minus 1th row of the original Liuhui triangle, and there you go. Now that's the new thing that's going to show up behind it if you keep shaving the new face off of the tetrahedron. So if you were to think this as like dice, right? I got my actual D&D dice over there. I think I got, yeah, that's fine. So you got your standard tetrahedron, right? Just shave a little piece of it off, and then off the face, and then the stuff that's right underneath it is going to be the ones you actually read off, etc., etc. So in terms of the triangle itself, y'all are having a completely different conversation. It's cool. I just looked over like, nope, that's not to me. Okay. So while they were doing that, I decided that I wanted to figure out what the pattern was for all of the individual... No, that's fine. So in the original triangle, right, you've got your 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, and it, apart from the messiness, no. No need to apologize. It's all good. As you start going down, what you're doing is to get every new number, you are adding the two numbers that are above it. Well, on the right here we have just the 1, and off to the left we have an infinite field of zeros. And the same is true on the right side out here. This is all zeros here, this is all zeros here. So, right. We don't have to worry about that stuff. So as we get deeper in, it's doing the same thing. So all these are just going to add up to those numbers down on the next row. Well, the simplex of any dimension is doing the same thing. So if I want to know what number goes in the center, well, in this particular case there is no center, but nonetheless, if I want to know what number goes near the center here, I need to look up above it and say, what is dropping into this particular location? Well, this is going to be back from this 6 on the row above, and it's also going to be in from this 3, and in this way from this 3, in this way from this 3. So the 3, the 6, and the 3 get us another 12, which is actually just set back from the other 12s. So this is kind of like a, if you were to rack a bunch of pool balls, right? This is an intersection of the 3 that are immediately above it, get us each of the 12s that are here, and each of those 12s is racking up against each other to form a triangle, a group of 3. Right, you do like shape packing and all that can help with some of this stuff too. Now, some of the interesting stuff that I found was that, well, it's not only that, like, over on the Liuhui side, the Pascal side that we usually know it as, if you want any particular number, like this 10, for example, this is actually the coefficient of the polynomial, binomial specifically, x plus y raised to the 5th power. And this is going to be the coefficient attached to the x squared y cubed term. If we go across, yeah, it doesn't really matter. You can do it either way you want. I think typically I start with x to the 5th on the left. Yeah, that makes sense. Right. So like x to the 5th is going to be over here, and then y to the 5th is going to be over here. Coming in, this is now 5x to the fourth y to the first, and 10x to the third y squared. Then it reverses them. You're counting up with the y's and down with the x's as we go to the right. So now this is going to be x squared y cubed, xy to the fourth, or again x to the first y to the fourth, and then here this is x to the 0 y to the fifth, and similarly before we had like a y to the 0 and x to the fifth. So it turns out, right, this is the coefficient for this binomial expansion. So if we want nth row for some, in this case, n equals 5, then we can get all those coefficients doing this. Makes it way easier. Right? And I assume that pretty much everybody who comes here probably has a passing familiarity with that much. It also turns out that that is the number of ways that a, for instance, plinko ball, pachinko ball, because plinko is a trademark, copyright, all that good stuff. So that is the number of ways that a pachinko ball could get from the top here down to, this 10. That's one possible path. There are 9 others. So if we then expand this out to the third dimension, then this means that to get to this 12 here, there are 12 different possible ways for us to have a ball that then goes through each of these things. So here, this is one possible way, is it goes just right. And then can we go backward to the 2, and then down to this 3, and then down to this 12. So it falls to the right once, back once, and then back again, and then forward, or left once. In order to get to this thing. So now we can actually expand this and start talking about it not just as, oh, this is going to be like our, A direction, B direction, and C direction. It's not just A, B, C as directions, as vectors. And we could do it as vectors if we wanted to. We could say, like, okay, this is going to get us, like I said, how many different ways could we get to this 12 here? Well, this is going to be, okay, what did I say? It was going to be, so the top is nothing at all, right? This is going to be our n equals 0 row. So no coin flips, no balls being dropped through the little maze that we got going on here. Okay, so the first drop goes from the null position at the top to C. So it goes down and to the right. Right, so the first one is C. And then the second one is going from the bottom right possible position, it is going up and back. So that's going to be our B position. And then the third one has to go up and back again, so that's our B position. And then in order to get from 3 to the next 12 there, it has to go in the A position. So falling right, back, and then left, or down left, is the way to, or is the first way that I've highlighted here, how to get from the top down to that fourth row. Okay, or we've got 11 different combinations that we can make that are apart from this one. So again, CBAB, and none of these are actually redundant, right? Because, right, that's taken care of. It's combinations. So CBAB, CABB, C. Nope, that's it. That's it for that one. So A, BBC, A, BCB, A, C, BB. Right, and there's only 3 combinations for that too. So then B, A, BC, A, CB, and there's 6 combinations here, because those last 3 are distinct from each other. All right, 1, 2, 3, 4, 5, 6. 6 here. And 3 for each of these. So with that being as it is, right, this gets us our possible 12 combinations. And in this particular case, this is now annotated as 12, nope, sorry, not 12. The value is 12, right? So those 12 combinations are going to be equal to, in this particular case, we had 4. Four choose, and in this case, it's 1, 2, 3. It's not exactly how it works, but oh, they'd hate me. Besides, I already found that this is well known. This is very well known. So the problem is reduced or generalized. The problem is generalized then as n choose k1, k2, k3 for however many dimensions you're working in. In this case, k sub I or whatever for I dimensions. Usually we use n for that, but because we usually do n choose k or n choose r or something like that, it gets all messed up because yay. But anyway, the way it works is you need I have the notation somewhere. N factorial going to be for right the number of permutations you can make of n distinct objects. So in this case we wanted 4 distinct objects, but it turns out they're not all distinct. So how does it work? Well, we need the product of I goes from 1 to 3 because we're operating in 3 dimensions. We are operating on 3 separate types of objects. And then that would be k sub I. K sub I factorial. Yeah. So, yeah, I discovered this by myself, and then when I got back to internet, I was like, of course it's, 100, 200 years old. Like, why would I even think that I had possibly discovered anything important? Hey, thanks for the follow. Okay, so if you really want the the thing that I was trying to find was, is there some sort of pattern to the sum of all of the items in this list? So 1, 2, 4, this is 6, 8. Now in this one, obviously there's a pattern. I know it. All right, 16, 32. All right, cool. Yeah, that one's easy. Now move down. It's 1, 3, 2, 4, 6, 7, 8, 9. Okay, so this one's just, again, powers of... There was a more important question, sorry. So let's just double check. 1, 2, 3, 4, 5, 6 is going to be 18 plus 6 is 24, 27. Yeah, okay. It's just powers of 3. Okay, so sum is going to be powers of whatever this is. Right, sum of rows is going to be the powers of top index. All right, whatever you want to call it. I'm sure there's a better name for it. It's fine. But that wasn't really where I was. My actual question for this, right, was what would happen if you didn't stop with just adding up 1 immediately above it? Yeah. So, yeah, this stuff represents a plus b plus c raised to the n, and then the appropriate, yeah, and then all of the appropriate stuff there. So again, I didn't actually end there. In fact, I wasn't even really interested in that, apart from just like doing it out for a few steps, because that looks cool. And then I was interested in, well, how do we do this for higher dimensions? Right, so how do we do it for 4th power? So a plus b plus c plus d. And again, this is not where I stopped, but this is just kind of an interesting thing. So I found out in 4 dimensions it becomes this. equals 0, n equals 1, n equals 2, n equals 3 is going to be 1, 3, 3, 1, 3, 3, 1, 3, 3, 3, 3, 1, 3, 3, 3, 3. Yep. Oh, do you already follow again? Brain. Come on, brain. Oh my god, why? This is not the right group. Where is my group? There we go. Megalomorph. I don't know who Brian is. Well, probably gonna have to check his stuff out. So. All right, memeing. I have played Firewatch. But yeah, Megalomorph. So he streams every so often. And I think has been off for a little while, probably due to summer, but man, all right, whatever, it's fine. So anyway, you construct a simplex for n-dimensional simplex for each step on the fourth. Oh, in the four-dimensional case. So creating a three-dimensional. Oh, we're creating a three-dimensional simplex on the fourth dimensional step. So it gets to be a bit confusing and hard to grasp reality when you're trying to do all this. That also should mean there's a hole in the middle which is filled by 6. You've got, in this case, all of these 3s that are immediately surrounding this. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh, so it won't be a 6. With all the 2s coming together, that should be an 8 now. Because there are 4 2s. Yeah, so it gets to be a bit more difficult. Oh, nope. There's more than that. Forgot the other 2 2s. Here and here. Those 2, those 2, those 2. 4, 6, 8, 10, 12. Yep. So it's not 8, it's 12. And this is in my original notes. I actually got it right. Anyway, so with the 12 there, Now this is going to say, okay, on n equals 4, this is going to be even bigger, more massive. The outside frame structure is still 14641. It's 100%. Alright, we still get 14641, but then as we're going, back, now we've got to fill in all these spaces, and this is where it gets really mind-bending and really hard to work out what all the faces are. Again, the faces here are actually not too bad, because we will get multiple of the original Liuhui triangle. So actually, it's even worse than I thought. Yep. The centers of all the faces are going to be 6s. And then there's a 12 in the center. Yeah, so again, like I said, it's just really complicated. So we got 4, 6. Should be 6 times 1, 2, 1. Which is going to get us 6, 12, 6. And then 4 times 1, 3, 3, 1 should be 4, 12, 12, 4. Which again makes sense because now we have a triangle of 12s, which are going to add together to get us the next turn. Like the next number that's in beyond that. And we all like some nice, decent symmetry. So anyway, that's also on the front face, and I'm just out of room at this point. So anyway, yeah, like I said, this makes it way harder, and that's only the faces of the this layer of the 4-dimensional simplex. So it gets more complicated. So anyway, the other place that I was going with this originally was, okay, now what if we don't limit ourselves to adding just the row above it? What happens if we say, okay, this is going to be, still our standard. You know what? Let's just even do it as a 2-dimensional one first. So we're going to take this and we're going to add the 2 layers above it to get the next one down. So for this one here, we're just going to go 1, 2 like this. These are the only numbers that contribute, so that number is going to be 2. All right, to get to the center position here, we can either go from the top left and down right, or from the top right and then down left. And in this case, we're just adding up the numbers that are in those 2 sets of rows, so that's just going to get us a 3. And then on the right side, this is just going to be a 2. Now, to no one's surprise, right, what's going to happen on the sides? This should be, instantaneous. Everybody recognizes what it is. I hope. 10 seconds to figure it out. just going to keep bonking the microphone. It's fine. Oh, you can figure it out. That's all right. All right, so if we add the 2 rows that are above this particular position, we're going to get a 2 and a 1. So that one's going to be 3. If we continue this pattern, the 2 rows above the next one are 3 and a 2, so we get a 5. And then above that 5, or sorry, the 5 and the 3 will add together to get an 8. 8 and the 5 will get a 13. So yeah, this is pretty well known. Everybody knows what that is. Oh man. Of course. So I attributed this to the Fibonacci sequence. We call it the Fibonacci, or I call it the Fibonacci triangle. Nobody else calls it that. It's fine. So then, again, on the outsides, this is super easy because it's just Fibonacci sequence, which, again, maybe should be attributed to somebody else because they found it first, but... All right, going on the inside of this, we've got now the 2 rows above this position are going to get us a 2 and a 3 immediately above it, and then a 0, 1, and 1 above that. So 2, 3 is 5, and then 6, 7. Yep. My students always love the rabbits analogy that the problem came from. Mostly because I think they like it. They like me being awkward or something, but choosing my words very carefully. All right. From this point, again, one of the other things we can do is actually just draw a triangle. And say, like, to get the thing that's in here, we can add up the stuff that's in the triangle. So here's a 0. 0, 2, 3 is going to be 5, and then the 7 and the 3 gets us 10, so 15. And then when we want to move stuff, we just can move the triangle. Oops. Then say, okay, what do we get here? That's way easier. So immediately above it is 14, and then 16, 18, and 3 is 21. And then we know it's already symmetric, so we can just fill in the blanks. You know, 0 effort here. I like low effort content. It's fine. Right, and then to get the next row down, do the same thing here. So 10, 15 is 25, plus 5 is going to be 30. So there is a bit of a problem with this, and you might be able to figure it out pretty quick. 10, 15 is 25. And 28 is going to be 53. And again, symmetric.